I'm pretty sure that most of you already know the answer. And the answer, of course, this is an acronym, and this is the French Conseil européen pour la recherche nucléaire, or the European Council for Nuclear Research, and it was established in 1953. So it is a very old, I mean, it's about 70 years old international organization. But you know, people, when usually they realize what CERN stands for, they always ask this question. So it's nuclear. So what do we do regarding nuclear power? You are making weapons, or how are you involved in nuclear business in the first place? So do you think that CERN is really a place where we actually, it is a nuclear plant? The answer is, of course, no. We don't get involved into that. Or do we have anything to do with atomic bombs or development of weaponry for military purposes? Of course not. So all we do is about exploring the nuclei. So just a bit of history. When in 1950s, they thought about the name of CERN, you know, in general, when they were saying nuclear energy, nuclear studies, that was basically embracing studies about the nuclei, okay, the substructure of the nuclei. And this is how the nuclear remained in the acronym, which nowadays seems to be a bit inaccurate with exactly what we do, because we don't deal with the nuclei, we deal about even the substructure of the nuclei, even deeper, maybe 1,000, 1 million times, you know, deeper than the size of a nuclei. So this is what we do. And actually CERN, let me make it clear, it's a European laboratory for particle physics, okay, not for weaponry. And it is stated very clearly in the proclamation that CERN won't never be involved in any kind of weaponry and development of, you know, military applications for military purposes and anything like that. So what CERN is today, because that was the mission, that was the idea 70 years ago. So what you see here, the yellow ring, that is the Large Hadron Collider. And this is the accelerator, which lies about 100 meters underground the Geneva area. And you see on that side, this lake, that's the Geneva Lake. And here, I don't know if you can see that very clearly, but here, that's the Geneva Airport. So this is a very big place, okay, the LHC, and this is the biggest experiment that humans have ever constructed and operated. And you see different other acronyms like LHCb. We have 4 big experiments which are hosted at the Large Hadron Collider. We have the LHCb, we have Atlas, we have ALICE, and we have, of course, CMS. And then here you see CERN Prevezan and CERN Meyran. These are the 2 main places where we have most of our buildings, okay? This is not a residential area. This is a place where we keep offices and some laboratories. So overall, you see that, and then you see this dashed line, which are the borders between France on the lower part of the screen and Switzerland on the upper part of the screen. So LHC crosses the borders between France and Switzerland, okay? And as I said, the circumference of it is 27 kilometers. Can you guess? Well, I'm pretty sure you can calculate what is the radius of the LHC. If you know the answer, just type it in the chat window. Okay, so over the years, the organization has hosted more than 140 experiments, different experiments of high energy and nuclear physics. Currently, we have about 20 different experiments running, up and running, active experiments, as we call them. And CERN's mission is to build accelerators, detectors, record, analyze data from the collisions, and also to transfer knowledge. At the very end, everything boils down to understanding the very nature and the laws of the universe. That's the main mission of CERN. It's not a place where it's not of applied physics, okay? It's about basic research. Okay, so regarding history, as I said, 1953, 1954, the first agreement was signed between the first 12 member states. 1957, we had the first accelerator built at CERN, that's the synchro cyclotron. Actually, if you ever happen to be at CERN and you get to be in one of these, you know, tours, which otherwise you would be doing right now instead of the virtual tour, you would be visiting that area. So this old synchro cyclotron, we keep it in a very nice room. Actually, it's in its original place. Of course, it's not operational anymore. And it was very, very important at the time. It was the first, as I said, accelerator that was built at CERN, and it gave very important observations and discoveries at the time. Like, for instance, we had the first observation of the antinucleate and anti-deuteron. Okay, 1973, bubble chambers. There were a lot of bubble chambers around CERN. It was the best technology regarding detectors at the time. 1976 to 83, the SPS, the Super Proton Cyclotron, tunnel was excavated. You see, it says 7 kilometers because, as I will show you later, this is yet another ring, okay, which is 7 kilometers of circumference. And the idea was to circulate and collide proton and antiproton beams. And in this tunnel, actually, we had two important experiments, UA1 and UA2, and those experiments gave us, in 1983, the discoveries of the Z and the W bosons, okay? And these discoveries were awarded with a Nobel Prize. However, because that never stops, we knew that already back then we would have to go to a bigger tunnel, and this is why in 1999 up to 2000, we had the Large Electron Positron Collider, and that was hosted in the same tunnel that we now use for the LHC. So just to clarify, the Large Hadron Collider is not positioned in a new tunnel. It is positioned in a tunnel which was previously hosting the Large Electron Positron Collider. And in 1989, another major breakthrough, of course, that happened at CERN was the WWW, and this is when basically we had the first website and server by Tim Berners-Lee. We can discuss about that a bit later. So these are just some of the highlights over the 70 years. Of course, someone would need many hours to go over all the major discoveries and achievements that have happened over the last 70 years at CERN. So who is CERN? Who makes CERN? So CERN is made from people all over the world, which are hosted in different institutes and different countries. So we have what we call member states. If there is not something that you need to say, can you please mute? Thank you. Okay. So we have a lot of member states, we have associated members, and we have a lot of international agreements. You see that few countries are not involved in what is happening at CERN. Of course, all these people, they do not work all at the same experiment and the same project, and they're distributed across all the different activities of CERN. So the budget of these are recent numbers of 2020. The budget for maintenance and upkeeping cost was about, I don't know what should best, but it's about 1.1 billion Swiss francs, or this is about 1.2 US dollars. So is this really a lot of money? So remember that this money covers everything, the maintenance, the running cost, the upkeep cost, logistics, personnel, paying salaries, and everything for the LHC. And if you think this is too much, actually per person, it costs only 1 coffee per year, okay? This is what it takes to do basic research of that caliber, okay? And I think this is very important to remember. So what we do, okay? As I said, CERN's goal is fundamental research, is not applied research. So for instance, CERN is not to improve how electricity is distributed or how rockets, are launched in space. CERN is here merely to help answer the questions and for a better understanding of the very fundamental laws of the universe. So let's take a step back and discuss about what was the primary idea of what matter is made of. So as you probably know, already very early, people have started to wonder what makes matter, and Democritus actually about 2,500 years ago, thought about you take a piece of matter and you start cutting in half, and again in half, and again in half, and you go to a point where actually you cannot have no more. So this is the quantity which he called atom. So atom, literally, it's a Greek word, and it actually means the thing that you cannot split further, okay? And we still use it today. So do you think that the word atom is correct for what we actually call atom? The answer is no, right? Because what we call now atom, we do know that there is a nucleus and an electron orbiting around it. And we took us few centuries, actually a lot of centuries, to realize that. So the word atom, which describes exactly this substructure, is not accurate. But this is, I think, historically, this is why we kept it like this, because clearly atom has substructure, so it's not really an atom, okay? So we have electrons and the nucleus, electrons orbiting around the nucleus, and then we realized at the beginning of the 20th century that actually even the nucleus has a substructure, and it is made from different protons and neutrons, those hadrons. And we were able, a few decades later, to go even deeper and realize that protons and neutrons themselves are made from even smaller particles, which are known as quarks. And then the question is, okay, are we done? What do you think? Do you think that quarks have inner structure? That's the end of the game? This is the best we can do? If you have any thoughts, just write them in the chat window and we can discuss them later. Okay, so there are two ways to proceed. As I said, you know, you have an idea, you try to implement something, and you put an experiment to test your idea, like what Democritus did. Start cutting something to smaller and smaller pieces. So he did a first experiment of particle physics, let's say. But then in our cases that we had theories, and we had to construct experiments to test the theories, like the special relativity or the general relativity. So in the end, that boils down to the knowledge that we have accumulated so far, and I will take you through the standard model of particles, of particle physics. So the standard model of particle physics, it's a theory, actually it's a very beautiful theory, which describes how elementary particles are interacting together through the elementary, you know, the four forces, actually three, because gravity is not described by the standard model, but the idea is that you have particles all over the place. You have 12 fundamental particles, matter particles as you call them, and then you have the different forces, and this theory describes how these particles interact among themselves in order to build matter. But do you know something? Actually, if you look around you or inside you, you will only find electrons and up and down quarks. So blue balls stand for what we call quarks. Okay, we have, you see, 3 different columns, and each one of the columns we have 2 different members. So we have the up and the down, the charm, the strange, the top and the bottom. But only 2 of them form stable matter. Those quarks with electrons. So again, take any matter around you, try to split it, and you won't see anything more than up-down quarks and electrons. So then the question is, what is happening with the rest of the particles? We do know that there are more than just the 3. So what happens to the rest of the particles? So the answer is simple. The rest of the particles are heavy, and once they get created, they tend to decay very, very, very fast. That's why you don't see them anymore free in nature. What has happened is during the creation of the universe, all of these particles were existing, but eventually they decayed down to lighter particles, okay? And then we ended up having up, down, and electrons bound together, forming matter. And of course, then we have the force carriers. You do know that we have, okay, I shouldn't say that. Can you write in the chat window how many forces we have? And do you recognize any of the photon, the gluon, and the Z boson? Okay, so I'm not going to say more about that. I would like to discuss that a bit later. Now, the idea is that each one of the particles still has what we call antiparticle. This is what you see with the dash on top of it. So all of these particles were created in many, in abundance at the beginning of the universe, but they are not all of them around anymore. And of course, what is really important is that also we have the Higgs boson, which was discovered at CERN and was announced in 2012. And this is just the particle which is responsible for attributing matter to every other particle. So the initial idea of the Higgs boson, it was actually predicted in 1964, initially by two Belgian physicists, François Englert and Robert Hood, and then also Peter Higgs completed the idea. So just look at the numbers. It was discovered, it was predicted in 1964, and it was discovered in 2012. This is about half of a century, 48 years later. This is how long it took us to be able to construct an experiment and test the theory that these incredibly smart people had 50 years ago. And that tells you something. It tells you that science is hard, and it is not always obvious how to test a theory. What we do know, though, is that in order to test theories that involve these tiny particles, you need very large quantities of energy, because you need to go deeper into the matter. Okay? Unfortunately, of course, that was awarded with a Nobel Prize only to François Englert and Peter Higgs. Ruth was not, had already this, and nowadays only Peter Higgs is alive. I mean, the old people anyway, but it's always sad to, when people are not with us anymore. Okay, so another idea, another thing that has been troubling us for a very long time is about what had happened at the very early moments of the universe. For instance, the quark-gluon plasma. Do you know anything about the quark-gluon plasma? So at the very beginning, just slightly after the Big Bang, so I mean, if you go back here, you see particles which are very distinguishable, okay? You can distinguish one from another because each one of these particles has its own properties, its mass, its electric charge, and so on and so forth. So you can tell because they have different particles. But really at the beginning of time, that was not the case. When the Big Bang happened, everything was very confined in an incredible amount of energy, and you could not tell one particle from another. Just imagine a very hot and dense soup. This is what the quark-gluon plasma is all about. That happened at the very early moments of the universe. And here at CERN, we actually try to replicate that form of matter because it would give us a lot of information about what had happened at the very early moments of the universe. This is the main object of study of one of the 4 experiments of the Large Hadron Collider, of the ALICE experiments in particular. We will see about the ALICE a bit later. And what about antimatter? Do you know what antimatter is? So antimatter is nothing more, or that's what we think, than taking any particle and just inverting its charge. So you have an electron. If you flip the sign of the charge from minus to positive, then you have a positron. But everything else is the same. Now, there is a mechanism that happened again during the Big Bang. We had amounts of matter and antimatter created. And you know what happens if you bring matter and antimatter very close, right? They will annihilate, and they will release a lot of energy. Now, for some reason which we don't actually understand, there was a lot of matter, a lot of antimatter, they were annihilating, but once every 1 million of these pairs, we had, imagine, just a bit of matter which was not annihilated with antimatter. And you know what? That's the reason why we're here today. Because we had slightly bit more matter than antimatter at the very early moments of the universe. So we really want to create some antimatter, and we really want to study antimatter, but this is very, very, very difficult. At CERN, we have a very nice way to do that. We have what we call the antimatter accelerator. This is known as the AD, which basically creates anti-atoms, and then it slows them down and eventually trap them in a very cold box, let's say. Of course, this picture has nothing to do with what we do. This is the picture from the movie Angels and Demons. Just wanted to, to trigger your imagination a bit. But what we really have is an experiment which flies, a detector which flies with the International Space Station. You see, this is the International Space Station, which orbits on top of Earth in about 400 kilometers. And it's not a really big detector, and this is about 2 football stadiums long. And the AMS basically is an experiment, as I said, basically tries to trace primordial antimatter from space, because what happens is that if you have a detector on Earth, of course, in between your detector and whatever comes from space, you have the atmosphere, and that dilutes a lot of the information that you have. So what is the simple approach? You just take your detector, you put it in space, and then you have nothing to interfere between the rays that are coming from space, from deep space, and your detector, okay? And what really happened, that was a very nice collaboration, which is still alive. CERN collaborated with NASA, so we built the detector, and then we shipped it to Canaveral, and then NASA put it in one of the shuttles, and they launched it, and they put it, and they installed it on the International Space Station. If you ever happen to be at CERN, actually, the AMS Control Center, it's a place of visit at CERN where people go and visit. Well, that happens when you come with a group, and they have, you have to organize that. But this is all I'm saying is it is possible to actually go and see the control center, which is a very nice experience, I think. Okay, so of course there are many more questions like dark matter. What is dark matter? So for example, if we look, very far away, galaxies rotating and everything, we see things which do not seem exactly right. So all I'm saying is that, if you actually look the evolution of the universe, and if you can say that this describes on the x-axis we have time, and then you see the Big Bang happened, and we have several different phases of the universe. So right now, we do know that if you account for all galaxies, all visible matter, everything that is included in our universe, not just our galaxy, if you sum all this mass, it accounts only for 4% of the total mass of the universe. There is still 96% made up from something which we have little information about, okay? What we do know, it is approximately 23%. This is what we call dark matter, and another 73%, it is about dark energy. Don't ask me what makes dark energy and dark matter. We have no clue. We haven't seen any experimental evidence. We do have some theories. We do test theories also at CERN. We try to detect, we try to have observations regarding dark matter, but with no success so far. In any case, we know that this is true, okay? Not more than 4% accounts for the total mass of the universe. So in reality, if you answer these questions, you may be able to answer also the structure and the evolution of the universe, and then, of course, give answers to these questions, okay? This is just to tell you that all the progress that we have made so far and in all the centuries explaining how matter behaves, okay, doesn't describe more than 4% of the total matter of the universe. So you really understand that the amount of the information and the knowledge we do know is really a tiny proportion compared to what we don't know. And this is what science is all about. Okay, so how do we do things? How things work? So let's take, for example, 2 apples, okay? And then imagine that you collide 2 apples. So at low speed, what happens? Nothing, okay? If you, however, do this bit more violent, maybe they will start to have some marks. And if you do that even more violently, most likely the apples will break in pieces. So this is exactly the idea. We take particles which have some substructure, we give them a lot of energy, so they gain a lot of momentum, we accelerate them really a lot, and then we smash them together. So how that works? Like that. So we accelerate the particles, okay? That means that they store energy, they gain momentum, they build momentum, then we put them in a collision, okay? And from that collision, basically, you can produce all sorts of fruits, not just apples. So you start by colliding apples, but in reality, you have the energy, you have then the potential to create all sorts of different fruits. And of course, that happens inside that detector. And the different, derbies, the remnants from the collision fly all over the place, and they hit your detector, and the detectors are like big 3D cameras, and this is how we detect and we know things. Okay, so this is a lot of math equations. Do you recognize a very famous equation? I'm pretty sure you do. And it's, nothing more than the famous EMC squared. And that is exactly the working principle of what we do. We have something with mass, we attribute a lot of energy, and then we create that to energy, and this energy then transforms back to mass. So we start with something, we give a lot of energy, they do collide. Remember, protons have substructure, and then given the energy you have, then you have the necessary kinematic threshold in order to start producing particles which are not existing so far. That's the working principle. Okay, let's talk about numbers, okay? Let's talk about the energy that it takes to do these collisions. So we do have the two proton beams circulating, and each one of the beams has 7 tera electron volts of energy. Do you know what is the definition of the electron volt? So if you take 2 plates and you charge them with 1 volt potential difference, and you allow 1 electron from, you let it go from one side to the other, so the electron will go to the other, will be attracted by the opposite sign plate. And while doing that, exactly because it is within the field, it will store some energy. How much energy? 1 electron volt. So 1 electron volt, it's a very, very tiny amount of energy. So we need a lot of energy, and we have the beams, and each one of the beams has 7 tera electron volts. So that sounds like a lot. Do you know actually how much 7 tera electron volts is? Well, it is not more than just a flying mosquito. Yes, you heard that right. So we do have basically the amount that a flying mosquito has, but what is the difference? The difference, of course, for a mosquito, this is significant, but when you distribute that energy and you squeeze it in a tiny space, we're talking about, millions of micrometers, okay? Basically, you have a very confined space with a lot of energy. So when you make the collision, this energy is available at a very tiny area. And that makes all the difference. The amount of energy released instantaneously, that gives you the possibility to do all these collisions. Okay, yes, so this is the number. This is just to give you some numbers. If you put the numbers and the zeros, this is how many protons we actually smashed it together. Okay, so this is an area view of the LHC. Remember, I initially showed you. So that's again the airport, the big one. That's the Large Hadron Collider. These are the borders. Okay, you see Switzerland and France. That's the Lake of Geneva. So here and there, this is Meyran, and this is Prevezan. These are the sites where we have most of our offices and some labs. This is where everything begins, okay? This looks tiny, but actually this is about 600 meters of circumference. This is where the beam starts rotating, and then it goes into this figure. This is the SPS. Remember, that was built in the 70s, and it is about 7 kilometers of circumference. And once the beam has a lot of momentum, okay, then we inject it into the big one, the Large Hadron Collider, for the final configuration, and initially, and then the collisions. Acceleration happens at one place. That means that the beam goes around, and every time it goes, it passes through this cavity, this area, it gets some boost, it gets accelerated more and more. And then in the 4 dots, we have the 4 major experiments: Atlas, ALICE, CMS, and LHCb. This is another diagram of exactly the complex. I'm not going to say more. The only thing that I want your attention, you see that the different infrastructures, they have 2 numbers. They have one date, and then they have, the circumference in meters. So you see this PS, the Proton Cyclotron, It was built in 1959, or the booster in 1972, the SPS, as we said, in the 70s, and the LHC was completed in 2008. So the message here is the following. It doesn't mean we start building an experiment at the time. Remember, the Proton Cyclotron was in the 60s, okay? So after its lifetime, it doesn't mean that we decommission and we throw away everything. No, we let's say, recommission, we upgrade, and then we plug it along with other complex in order to, to be able to produce higher energies. So basically, the beams start from here, what is called LINAC 2. The beams are produced, they are injected into the booster, they start circulating, they get some momentum, then at the next stage, they get some more momentum, and so on and so forth. By the time they are injected here, they are running with 99.9 the speed of light. And by the time they are at the LHC, they are running with 99.99999 the speed of light. I just remind you that the speed of light is 300,000 kilometers per second. So do you understand practically? Let me go back to this one. So practically, if you have that speed, and this is 27 kilometers of circumference, if you divide, you will see that basically the beams go around the LHC tunnel more than 11,000 times per second. Just take a minute to realize that, okay? 27 kilometers, you can do that more than 11,000 times per second. That's how fast the beams travel. Okay, but how we make proton beams in the first place? So the idea is simple. You take a plain bottle of hydrogen. It's exactly like you see here, okay? We take hydrogen, which is pretty simple. We just strip from the protons, we take out the electrons, and what remains, you have your protons. Then, of course, the protons are grouped. We have to do that again and again. We have to build the bunches, a lot of, billions of protons. And then the protons are guided through a sequence of several different, as we explained, boosters in order to be momentum. And then eventually they are injected into the LHC to collide. So do you know what is the coolest place in the universe? Not on Earth. Actually, it's on the universe. It's wrong what I say. What it says here on Earth is wrong. Actually, it's on the universe. You guessed that right. It's CERN. Let's see why. This is most likely you already know the answer. That has to do with the magnets, the superconducting magnets we were using. So everything started, of course, by preparing the LHC. It took a bit of, of time to excavate. Again, the tunnel was the LET tunnel that later on the LHC was hosted. But of course, we had to build big caverns, big holes, which would fit the big experiments. We built all these big magnets. Each one of these magnets, this is a dipole magnet. I will show you more about that later. And we have this very nice facility, the SM18. This is the place where we take all the magnets and we test all the magnets. And this is very, very important. Again, SM18, it's also another point of visitation. If you happen to be at CERN with a group, most likely you will also be able to visit that place. And of course, each one of these magnets had to be lowered in the tunnel and transferred, okay, in its final position. Remember that this access hole is not all over the place. There is only 4 or 5 access points, and then you have to really travel the magnet inside and put it in its final position in the tunnel. So the magnet, we do have more than 1,200 of dipoles and about 400 of quadrupoles. I'm not going to bore you with the technical details. We can discuss more if you like later, if you have the time. But the idea is that what I want to ask you, do you understand why we have to keep these experiments, why we need to go underground? And even more, why the cavern, why the tunnel, not the cavern, why the tunnel has to be that long? 27 kilometers of circumference. Do you know any of these answers? If you have an idea, don't be shy. Write something in the chat. I want to discuss this later. Okay? Okay, so about the magnet, how the magnet looks like. So again, this is a diagram. You see the 4 points, Atlas, Alice, LHCb, and CMS. So you see 2 lines, one red and then one blue, right? And you see here, the blue and the red interchange. Why? Because the beams travel in parallel trajectories, and only in these experiments you have to cross them in order to have the collisions, right? So they go like this, they travel, they meet, and they continue traveling. So the two beams, we have two beams, 7 TeV each one. In total, we have 14 tera-electron volts of energy. We have a very, very strong magnetic field. We use the Lorentz force here to bend the beams. And this is exactly what I told you that's the coolest place in the universe, because in order for this machinery to work, we have to keep everything at very, very low temperatures. So why we need to do that? Why we need to do that? We need to do that because exactly in order to achieve that high magnetic field, and the magnetic field basically produces a force which forces the particles to bend. That comes with how strong magnetic field you have. And to have the magnets really performing that much, you have to cool them down, because it is only then when they really manifest their properties, okay? Superconducting magnets. That's why you need a lot. And basically, the superconductors are powered by 12,000 amperes. Do you know how 12,000 amperes compare to, our day experience? Remember that in your house, if you look the board that has all these fuses and everything, if you sum them up, most likely it won't be more than 40, 50 amperes. And in each one of the magnets, we need to power them up with 12,000 amperes. Okay, I will come back to the helium cooling a bit later, but I want also to mention that exactly to ensure that the beams go unimpeded, that means with no colliding with any residues, any molecules, any air molecules, or any dust. Of course, the center, well, the whole of it, but most of it, most importantly, the center of these magnets have to be kept at very, very high vacuum. How high vacuum? It's about 10 to the minus 13 atmospheres. I mean, this is 0.0000000, okay? Just write down. You will see this is an incredibly small number. Actually, that vacuum is 10 times less than the emptiness on the surface of the moon. So I would say that even that number is the most empty space in the whole of the universe, okay? And this is an amazing technology behind that, of course, to have pumps that could really produce that vacuum in the first place. So now for the temperatures, as we explained, you need to go very low exactly to allow the magnets to start performing well. And we have to reach minus 271 Celsius, which is 1.9 Kelvin. This is 1.9 Kelvin above absolute zero. So basically, if you go to outer space, if you measure the temperature of the outer space, you will see this is a bit warmer. This is 2.5 Kelvin. So we have here the machines which go really, really lower even from the outer space. So LHC, it's doing that by using cryogenic facilities, and any given moment when the machine, of course, is operating, we have 120 tons of helium circulating. This is about 700,000 liters of helium circulating in the magnets. Okay, so these are some pictures from that's the Atlas detector. You see people working on one of the wheels of the detector. You see. I just want to get your attention on the scale of these experiments. So you see here just a human being. You see a guy standing over there, and you see a drawing of the Atlas detector, and you see this is an average person. So this is really huge. And it's huge because it's about 50 meters long and actually more than 25 meters the diameter. And the different colors correspond to the different mechanical parts, what we call the sub-detectors, because you need different components, different things to detect and record different kinds of particles. So you need a very complicated machine in the end. And this is also some pictures from CMS. This is my experiment. CMS is definitely smaller. It's about half the size of the Atlas detector, So why we call it CMS? CMS stands for compact muon solenoid. Let me explain about the compact. Imagine that this detector, it weighs about 2 times the weight of the Eiffel Tower, okay, 14,000 tons, but it is still compactified in a region, in a volume 12 times less. This is why we call it compact, because it's very dense. And all these beautiful colors you see, this is because of the different sensors that we have, which are used again for, you know, detecting different particles. So this is the beam pipe. This is where the beams come. You see, it's really tiny. It looks very tiny. The different colors here, you have the electromagnetic calorimeter, the hadronic calorimeter, the magnet, and then the muonic stations. Okay. Again, as I said, Atlas and CMS are the big collaborations. They gather about more than 3,000 scientists all over the world each. And this is just amazing. And then we have ALICE and LHCb. These are no general purpose experiments. That means that they were built with having a very specific idea in mind. The ALICE experiment was built around the idea of studying what we talk about the quark-gluon plasma, and the LHCb experiment was built around the idea of studying beauty physics. Beauty physics, we think, can give answers to the asymmetry that we discussed about matter and antimatter. So we try to see if what we measure really fits what we, theory, and if there is some disagreement there, that could be hints for new physics. And we do have some hints for new physics, but physicists like to be very, very careful before announcing anything. Now, this is not to say that ALICE and LHCb are less important than ATLAS and CMS. They are equally important for LHC and the physics program we have. It is just they're just smaller, but it doesn't mean less important. And again, they also gather a lot of people, a lot of institutes from, I don't know, maybe 20 different countries and 7 different universities, last time I checked. Maybe now it's even more than that. So how do we do things? So you have the beams, they collide, and then they start breaking, and the derbies, they fly all over the place. They start hitting your detector. The detector is like a 3D camera with 100 megapixels of resolution, and it takes many pictures per second, and every 25 nanoseconds, you get new protons inside to collide. So this is static, but what you can see the tracks of the particles flying inside out the detector, and you can clearly see here, for instance, a muon hitting what we call the muon stations, and the green bars over there stand for energy which has deposited on that part of the detector. And of course, the more, the larger the bar, the more energy sits on that part of the detector. So we take these pictures, billions of these pictures, and we try to analyze them. Of course, not as photographs. We have raw information of momentum, energy, position for each one of these particles, and this is what we do in our real life. So if you want to put some pictures in that, I think these are more realistic. Can you see the motion? I hope you can see the motion. These are some GIF pictures. Hopefully you can see them properly. And you can see that you get the helix because, do you know the answer? Do you know why you get particles flying like this with a helix? It's because they do have charge, and of course, because the detectors are within a magnetic field. And this is how particles having charge will fly, okay, outside your detector. And this is, if you rotate the detector, you see how basically different particles look like in the detector, and even more denser if you collide heavy ions. So in reality, we take all this data, we analyze them for years, and then we try to see, let's see how things look like. So we do have models which we plug in. We say, nature works like this, and we make predictions. And then we open our detectors and we take pictures. We see what nature gives. And we start comparing our predictions with what we really record. And then you can say, for instance, let me explain what you see. Basically, you see the plots that were used for discovering the Higgs boson. On left by CMS and on the right from ATLAS collaboration. So what you see with solid blue, this is our prediction. These are the models that we have given the processes that we know that exist in nature. what in what we call, this is an observable. We pick a variable, we pick something, and then we plot, okay? So this is the invariant mass of the 4 leptons, presumably coming from the Higgs boson. But the problem is that you may have many, many different processes in nature that can give you 4 leptons in the end, okay? So you see all this blue stand for different processes, but not the Higgs. And the Higgs is just this red one. This is our prediction. This is what we thought that it should look like. And then we open the box. Let me go through that. And you see, it goes from, from 0, and it builds up, because this exactly corresponds. You see this number over here. It tells you, because that goes with how much data we started to accumulate and record. And you see, it started to become more and more and more evident that actually we have seen the Higgs boson. So black dots, as you understand, correspond for what nature gives. Okay, that's data. And you compare your model, and then you know within some certainty, of course, it's not simple like that. You have confidence levels, you have to do a proper statistical analysis. It's not like having the plot and deciding yes or no. And basically, on another plot, this is the invariant mass from a different possible decay of the Higgs boson. This is to gamma gamma. And you see that the blue line corresponds to everything else, what we call standard model processes. And the red one corresponds to what Higgs looks like. And this bump over here told us that indeed we have found the Higgs boson. Okay, I think this is very exciting. And if you pay more attention, you will realize that actually that plot became reality. Actually, it was completed after many years of data taking and proper analysis. So how do we do things? What are the tools that we use? So we have developed a grid, the LHC grid, which is the largest computing grid in the world, of course. And you see on the map over here, you see several dots and lines. Each one of the dots corresponds to a computing center, let's say, all over the world in different areas. And all these dots, of course, connect. So the idea is that you have in your possession as a physicist to analyze, you have millions of cores, and then you do your analysis. Basically, it's like the light in your room. When you switch on the light, you don't really care where the power comes from. You only care to have electricity in your room, right? So this is exactly, when I analyze something and I sit here in Geneva, I don't really care if my data was analyzed in Italy or in Spain or in Pakistan, or all I care is to have something on my screen. So this is how it works. It distributes the load, and we have more than 250 million cores available to do our job. And this is also a thing that has helped other spin-offs and other projects to become better regarding computing facilities all over the world. Okay, so what? I mean, that's nice. You do science. That's totally fine. So you may wonder, is this something useful for me on my everyday life? Well, definitely the answer is no. The answer is no on a daily basis. If I find the Higgs boson today, we found the Higgs boson, your life didn't change the week after or 1 month after we found the Higgs boson. The idea is the following. For us to come to the point to find the Higgs boson, we had either to improve existing technology or invent new technology, which eventually, became available to you. Have you ever wondered, for instance, you have a mobile or a laptop. After a couple of years, this seems to be old, right? You see, companies tell you now you have to get the new chip, which is faster, which is more performant, and so on and so forth. It is exactly the same. We also invent a technology, and this technology, the member states that also develop at CERN, then they take back at their home institutes. So this is how CERN works, okay? It's a big transfer knowledge center, I would say. So let's review some of the benefits for society, clear benefits, something that everybody can understand and relate to, okay? For instance, we have the World Wide Web. That was developed initially as an idea, as a protocol, because, physicists wanted to share information, and it was not very easy to do that. So Tim Berners-Lee came down with a protocol, and it was developed in 1989. And, probably most likely, most of your generation, people of your generation, when you were born, CERN was a thing. You didn't have to think about that a second time. But people of my age, of course, we know how life was before web. So this is something that came, I think, very how to say that. CERN had definitely a major contribution into that. The protocol, of course, the idea of communicating remote places, it was not from CERN. It was only the intranet, which was already from the 60s, from the US Army. But really, the protocol that allowed computers to communicate all over the world was invented at CERN. And of course, as I said, CERN is not about physics only. Okay, we have many different things. We have, as I said, technology. One of the first touch screens were invented at CERN, actually. Most likely we didn't know that. Okay, we have many different applications on medicine, like the medical imaging, PET scan, hadron therapy. CERN is deeply involved into projects that promote and improve the technology regarding medical application. And we have many education and labs, school labs, for instance, for pupils and students who can come here, live here at CERN for a few weeks, and be also physicists and build things with your own hands. And of course, this is a very nice environment because it brings people together from all over the world. And I invite you to question yourself: why do you think CERN has succeeded working for the last 70 years? You see, around us, there is a war every second day, right? People killing each other for nothing. But CERN, for some reason, has managed to unite people over the last 70 years. And I remind you, you have people from different cultures, different religions, different ages, different, whatever. Why? How that was possible? I can tell you why. Because at CERN, we care about science, not personal beliefs. We do not care about what you believe, what you think. We only care about science, and science is about what you can measure and qualify, not what you think it is. And everybody understands the difference, and that's why I think CERN has succeeded over the years. Okay, there are of course other projects like humanitarian missions. For instance, CERN hosts the UNOSAR, which is a UN agency, and with the computing power that we have, what we do, we take pictures from satellites. For instance, and CERN was really able to say, it looks like there is more need to act on these places first. And if you had the teams on the ground trying to do this assessment, it would take them hours, if not days. So we do that every time there is, a disaster. CERN can really analyze very fast satellite images and really help the humanitarian missions where to act first with a lot of precision. I mean, you see here, for instance, you see a lot of mud roads, blocked roads. So CERN really was able to point people where they should focus first. Okay, so I think I'm done. In a nutshell, CERN, it's about fundamental research. It's about the largest, basically, international collaboration, scientific collaboration. And of course, it's about technology transfer and benefits for society. So that was all. Thanks for your attention. Of course, if you want to learn more, there are plentiful of sources on the web, home.CERN, visit CERN, career CERNs. If you think that this is for you, why not? And please do not forget to fill up the survey. So thanks for your time. It is about 4.3 kilometers radius because this is 2 PR, so you can do easily the math. So it's big, right? It's a big area. EMC squared, correct. North Pole in our Earth. I'm not sure about what is this about. Okay, yeah. So an idea why it is 27 kilometers long. Exactly. Again, it comes with how much energy you want to attribute to your particles. Okay, and if you are confined within a small magnet, a small area, then you cannot attribute a lot of energy, because exactly the Lorentz force will push the particles to go to move to a circle with higher radius. So you need to have bigger tunnels if you want to go to higher energies. Okay, and this is why after the LHC, which is 27 kilometers, we are actually already planning building the next generation of the Hadron Collider. And this will be about 100 kilometers, the circumference. And we hope to build that in the next 30 years. So you see that never stops. And that will allow us to go about 7 times higher in energies, times 7, that means the energy that we have right now. The idea is to go about 100 TeV, the energy of the future accelerator. So there is a lowest temperature 0. We can't go lower than that, but is there any specific reason to why there is not the highest temperature like that beyond which we can't go? I'm not sure I understand the question. So indeed, minus 273, okay, 0 Kelvin, that's the lowest you can go. Yeah, so that's the lowest we can go. And we go down to minus 271.3. And if the idea is that why you don't go lower than that, actually we do. Actually, in this antimatter accelerator, in this antimatter facility, we go even lower, because when you have the antimatter and you want to try it, you have to be really, really cold. You go even lower. But, you know, at some point, as you said, there is a lower value which we can achieve, and we're very close to that. So, next question. If we increase the tunnel length from 27 to more, it is possible to get a better result from the experiment? I think yes, definitely yes. So there are 2 ways to improve. If you have to keep the same tunnel, you can put stronger magnets. Or you go to a bigger tunnel and you use the magnets that you were using before. Ideally, you go to a bigger tunnel with stronger magnets. And this is what we will try to do next. But exactly that's the idea. Bigger tunnel, bigger magnets, more energy, better collision, more energetic collisions, more information. Because you see, how much we go deep into matter, it's like a microscope, is inverse over the energy. That means the higher the energy, the smaller the wavelength we can achieve, if that would be a microscope. So you need high energies in order to go deeper and deeper and deeper and deeper. And this is very, very difficult. So definitely the answer is yes. Bigger tunnels mean really improvement in the final result. Okay, is it possible to understand the exact mass of top quark by CMS? Yes, actually the top quark has been discovered in the 90s, and CMS is one magnificent machine that has given very, very accurate results lately of the mass of the top and the width of the top, of the properties of the top. There are many, many public results. So, you know, top physics, it's very interesting for 2 reasons. First of all, because it's the heaviest quark of all the 6 quarks, as you know. And it also decays before it hadronizes. That means it's very special how we treat it. It's very heavy, and that also connects maybe to new physics. So we have a lot of different analysis going on top physics, and a lot of results published already on top physics. And you can find all of them on the web. Do you allow foreigners to visit your area? I'm not sure I understand the question, in the sense, you mean visitation, you know, just to come and visit CERN as a tourist? If that's the question, the answer is definitely yes. I mean, you can book a visit group. Now we don't do anything else than, you know, these virtual conferences. But in normal, apart from COVID, what was happening up to 1 year ago, and what we hope will happen also from September or October onwards, we organize many groups every day. Basically, we have about 120,000 visitors every year, either in schools or people that come to spend some time at CERN. So if you come with a school or a university, typically there is half day reserved for you, and you get to see many different places. If you come alone, then you can go in what we call open visit. This is a 2 hours visit, again, with a guide. And there are also other places which you can visit alone. You can walk in and, exposition center and all these things. You can find all this about visiting CERN. All of the information are online. So definitely, yes. I mean, and just to clarify, there's no such thing like foreign here at CERN. I mean, we don't separate people by being a foreign or not. Who is a foreign? I mean, whoever is not a Swiss. I mean, okay, it makes no sense. But I see your point. You wanted to ask if so everybody can visit CERN. Yes, that's the answer. Okay. Any more questions? Are a minority. Most of people working at CERN are not physicists. I am a physicist, but most of people are not physicists. We have really a lot of engineers, okay? And there are several different programs, apprenticeship programs, summer student programs, fellowships. So online, if you go to careers at CERN, you will be able to find all the information. If you won't be able to find, there is also some contact mail. You can ask them, look, this is my degree, where you think I could apply? They would be happy to help you. So definitely you have a relevant degree and you could be part of that, right? So for NASA, I cannot tell you. All I can tell you is that typically NASA does not hire non-US citizens or people with a green card. So NASA, it's also a different continent. It's not my field, but I do know that non-US citizens, usually they don't get hired due to security concerns. But for CERN, usually nationality, it's about qualification. So if you have good grades, you have good letters, and there is something that really fits your qualifications, you could be a strong candidate. On the other hand, keep in mind that a lot of people want to be here at CERN, right? So don't be disappointed if you apply and you don't get a job, you have to apply again. It doesn't mean that we are not good for a job at CERN. It is just to be right place, right time. So don't be discouraged if you people try and you see, oh, it's too difficult. Yes, it is difficult, of course, but it doesn't mean that we don't have the qualifications. Maybe at the exact moment there was someone with better qualifications, or they were looking someone with, slightly different things in his CV. So I would say study hard, have a nice CV, be able to defend what you have been doing in case that people, you get an interview, and don't be afraid to try, okay? That's the only, there's no magic solution. You have to try.
Yeah.
To go back to their country and they were not able to come back given the travel restrictions or the situation in their countries. Even now at CERN, we don't go if we don't have to go. Okay, so definitely, the rule is that safety first. Nothing is more important than the health of people, right? But of course, several people have been affected. what I do know is that we didn't have that many cases at CERN. It was mainly from contractors and everything. People are very careful anyway. You are not allowed to walk without a mask. You are not allowed to walk, even in the restaurant. There is only one person every 3 meters. We have all these sorts of rules to keep people safe. So we hope that very soon things will, the more people get vaccinated, things will come back to normal, maybe from fall onwards. Yes.
Yeah. So thanks, sir, for giving us opportunity to attend such an important webinar. So I think, it's very important for our students, and they may learn a lot of things about CERN, and it's a very good opportunity for them to learn about CERN.
Definitely.
So thanks again.
And as I said, my advice to your students would be not to be shy.
Yeah.
They have to be good. Have some good grades, in the sense they have to know their subject. Grades are not important for someone. A number on a paper, okay? Okay, it's something, but you have to understand that this is not what people care about. They really care to know that you know your topic, you're a good person, someone who people can work with and collaborate with. That's, other qualifications that you have to develop as a professional. Okay.
Okay, thank you.
So thank you very much for joining.
Yeah.
Stay safe, everybody.
Yeah.
And we hope to see you again.
See you again. And we'd like to say thanks on behalf of the Department of Physics, Permanent University of Science and Technology, for accepting our invitation, sir. So thanks.
Thank you very much.
Yeah. Bye for today.
Okay.
Bye.
Take care.